Hello and welcome to Chem Clips by Mr. B. In this series of videos, we will be focusing on developing your exam technique for A-level chemistry, and our approach to this is going to be extremely straightforward. I'll be selecting a few past paper questions per topic area, or for a number of topics, and for each video upload, I will attach these as a document for you to download. For example, in this clip, you'll find a link in the description box below to download the past paper questions. Now, our approach is really straightforward. Once you've downloaded the questions, my suggestion is you pause the video at each point where we approach a question. For example, you pause it at question 1. You do the question yourself on the hard copy you've got, on a piece of paper, whatever, it really doesn't matter. Once you've done this, play the video, because I'm going to model how to answer the question and I'll have a running commentary associated with this. So hopefully this will prove really useful for you in understanding how to tackle an exam question, what to look out for, common mistakes, etc, etc. At the end of the day, it's extra practice with some further support. Anywho, in today's session, we're going to be looking at atomic structure, isotopes, and formulae. So let's get cracking on. By the way, this is for the OCR exam spec. This will work for other exam boards, but I want you to understand this is tailored to OCR. So let's get cracking on. We're going to start off with topics 2.2.1 to topics 2.2.2 from the specification. Okay, anywho, let's get cracking on. So we've got antimony, and antimony has an atomic number of 51. You're told that it exists as a mixture of isotopes. Now, for the first question, for 1 mark, you've been asked what is meant by the term isotopes, and it's only a 1 marker, and it's a definition that you need. Now, you're thinking straightforward, well, this is really easy, this is in GCSE, and you're right, it is, but there's a certain point that students often miss out, so let's talk about it. If I had, for example, carbon 12, carbon 13, and carbon 14, these are all isotopes. They're all isotopes because they are atoms of the same element. The only thing that's different with these is that each carbon atom has a different mass number. So we know that the smaller number represents the number of protons. The larger number, the mass number, represents the number of neutrons and protons. Therefore, the only thing different between the isotopes is the number of neutrons. So that part's really straightforward. So we're going to start off by answering atoms of the same elements with a different number of neutrons. Now, you'll feel that, many of you will feel that, you know what, that's fine. And to be fair, it is. But in certain exam questions, on certain exams, if you look through past paper questions for isotopes, you'll often be asked to add something else to this. So we've established that it's got a different number of neutrons. So what else is different? What is meant by the term isotopes? Well, the only thing that's different is they've got different mass, because their mass numbers are different. So we're going to state atoms of the same element with a different number of neutrons and different mass. Now, you don't need both in this particular question, but it's good to get into the habit of understanding what the examiners are looking for, okay? So, difference. Sorted. 1 mark, easy. Not a problem. Okay, moving on to the next question. Different isotopes of antimony have the same chemical properties. Explain. So we need to, in our answer, give a reason for this ultimately. So why is it that isotopes have the same chemical properties? Because we've established they've got a different number of neutrons. So what's going on? Clearly, the number of neutrons doesn't affect the chemical properties. Well, chemistry is all about the study of electrons. The reason it has the same chemical properties is because isotopes have the same number of electrons. If you've got the same number of electrons, surely its chemical reactivity will be the same. But you know what? It's not good enough to say that it has the same number of electrons. We need to be really specific. So you need to state that it's got the same number of electrons in the outer shell. Or you could otherwise mention it's got the same electron configuration or the same number of valence, with valence meaning outer electrons. So I'll write down for this question, isotopes have the same number of electrons in the outer shell. That's it. That's all you need. Easy, right? Okay, another mark. So, part 3. Complete the table below to show the atomic structure of a 1,2,1 antimony. So, I'm going to have a look at my periodic table. I'm going to identify what the number of protons are. What is the atomic number? So, antimony has got 51 protons according to my periodic table, and on the OCR periodic table it shows up as, it has the mass number at the bottom, or the relative atomic mass at the bottom. So, and on the periodic table it shows, well, it shows another number, 121.8. However, seeing as the question gives me a 121, we'll stick with 121. Okay, so we know that the small number is the number of protons. So clearly we've got 51 protons. We're going to, now in an atom is neutral, so it has the same number of protons as it does electrons. So we're going to have 51 electrons. To work out the number of neutrons, we're simply going to do the mass number, or in this case it's the mass number, minus the number of protons to give us the number of neutrons. So 121 minus 51, 70. Again, really straightforward. And there's nothing different in this compared to GCSE. However, you would be astounded at how many students get this wrong in an exam. And it's not because it's difficult, it's because in an exam it's quite stressful. It's not the easiest of an environment. So it's really important to take your time, stay calm and collected. You don't want to be losing marks like this willy-nilly. Right, moving on. So we've had a look at question 1, really straightforward, nothing difficult there. Moving on to question 2. You've been told that bromine has 2 isotopes, bromine 79 and bromine 81. You've been told that the relative atomic mass of bromine is 79.9. You've been asked to calculate the percentage of bromine 79 in a sample of bromine. So how are we going to tackle this question? Well, there's this formula you need to know, and the formula shows or tells you how to, or allows you to work out the relative atomic mass. So what is the formula? Well, firstly, let's start off with relative atomic mass. Relative atomic mass is often given the symbol capital A subscript R. Now, to work out the relative atomic mass, you have to multiply the percentage abundance of isotope number 1 multiplied by the mass number of isotope number 1, and you have to add this to the percentage of isotope 2 multiplied by the mass number of isotope 2 plus number 3 multiplied by the mass number of isotope 3, etc., divided by 100. So let's have a look at what information we've got. So I'm going to start off with the formula to begin with. Now this formula you need to know. It's not provided to you in any exam, so you must learn this and commit it to memory. Again, it's just GCSE chemistry, and I'm confident that you can do this. So percentage of isotope 1 multiplied by, we'll write down the mass number of isotope 1 plus the percentage, well, that's not a percentage symbol, percentage of isotope 2 multiplied by the mass number of isotope 2. Now I'm going to limit it to 2 because there's only 2 isotopes in this, bromine 79 and bromine 81, divided by 100. So now it's a matter of subbing the data. What do we have? Well, we're told that the relative atomic mass is 79.9. So I'm going to sub 79.9 for AR. Okay, now we need to, if we look at the formula, we've got percentage of isotope number 1. We are not given the percentages of either. So if we do not know what the numerical value for the percentage is, let's use algebra. Let's use algebra, and I'm going to state that the percentage of isotope 1 can be given the symbol X. So X. We know the mass number of isotope 1. Now we're assuming that isotope number 1, I'm going to assume it's bromine 79. You could do the same for 81, it doesn't matter. However, I'm going to do for 79, I'm going to use it as bromine 79. I'm going to identify that as isotope 1. So multiplied by 79 plus percentage of isotope 2. Now, what is the percentage of isotope number 2? Well, for isotope number 2, as we've committed that the percentage of isotope number 1 is X, it so follows that our percentage of isotope number 2, seeing as all percentages add up to 100 and we've only got 2 isotopes, will be 100 minus X. That is our percentage value of isotope number 2. So we've got 100 minus X multiplied by 81. We're going to divide that by 100. So let's begin to simplify this. If I take 100 to the other side, I'm going to multiply by 79.9. It's going to become 7990 is equal to, now 79 times X is 79X plus, so we've got 100 multiplied by 81. So we've got 81, 0, and we've got X or minus X multiplied by 81. So that's minus 81X. We've already taken the 100 to the other side. So now again, let's gather the like terms together. So I'm going to move the 8100 to the other side. So 7990 minus 8100 is equal to 79X minus 81X is minus 2X. So that's equal to minus 110 is equal to minus 2X. Therefore, X is equal to minus 110 divided by 2. So that gives us, divided by minus 2, sorry. So that gives us, in this case, 55. So X as a numerical value, as a percentage, that represents isotope number 1. So the percentage of isotope number 1 is 55%. And it so happens that I chose that X denoted the percentage of bromine 79, which is what the question's asking us. Calculate the percentage of bromine 79. So we've got this, it's 55%. So you're going to be given a mark, awarded a mark for this calculation and subbing the data into the equation. A lot of students won't show the working out, and it's really simply because it's not because they don't understand it. It's simply as a, from my understanding, it's a time-saving feature for the students. But please make sure that you show your working out. What is going on? Why is it? So you're going to get a mark for showing the equation and subbing the data in. A lot of students miss this out. Not because, again, it's hard, but simply because they feel it's a waste of time in the exam doing it. Don't. It's really important that you recognize that you're doing this anyway. Show you're working it out. It's really important that you're not losing marks for choosing not to show working out. That is one of the silliest decisions you could make in an exam. And you're going to get a mark for 55%. So again, really straightforward. Okay, moving on to question number 3. You're told that bromine and mercury are the only 2 naturally occurring elements that are liquids at room temperature and pressure, so RTP. Some physical properties are given in the table below, and you're told its appearance, its melting point, its boiling point, and its electrical conductivity. So again, it gives us information that infers the intermolecular forces and the bonds for, well, the bonds in terms of mercury being a metal, and thus it's a good it's a good conductor of electricity. Anyway, you're told that element X melts at temperatures reached on very hot summer days, yada yada yada. Okay, so let's just highlight that because we're talking about element X. A sample of element X was analyzed by mass spec, and the mass spectrum is shown below. Calculate the relative atomic mass of element X. Give your answer to 2 decimal places. So we're doing the same thing as what we did in the previous question. We're working out the relative atomic mass, so we have to use the equation AR is equal to the percentage of isotope 1 multiplied by the mass number of isotope 1 plus, do the same for isotope 2 and 3 or 4, whatever, divided by 100. However, this time we are presented with the data in a different format. We're given the data in a mass spectrum. Does this make a difference at all? None whatsoever. And it's important that you recognize that despite the data being given in a different way, it has no impact on the calculation. So let's do this. AR which is what we're working out, is equal to the percentage of isotope 1. Let's go with 72.17 is the percentage of isotope 1, assuming that 85 X is isotope 1. So ultimately the mass spectra tells us we've got 85 X and we've got 87 X. So we're going to assume that 85X is isotope 1. Again, it makes no difference which one you choose. So that means I've got 72.17% of isotope X. So I'm going to do 72.17 multiplied by 85 plus 27.83 multiplied by 87, all divided by 100, and let's see what I get for an answer. So I'm just going to put this into my calculator. So I've got 72.17 multiplied by 85 plus 27.83 multiplied by 87 divided by 100, 85.5566. Now, because we've got this answer, and firstly it's already to a ridiculous number of sig figs or dp, we're told we need to give the answer to 2 dp. So if we read the question, it's there. In fact, it's in bold. But again, you'd be surprised at how many students miss this out in the heat of the moment. So 2 decimal places. Let's show this. Therefore, it's going to be 85.56. It's that simple. It really is, folks. 2 marks for that again. 1 mark for the equation, 1 mark for the final answer to 2 decimal places. Okay, now we're asked to identify or suggest the identity of elements X. How are we going to do this? Well, I know what the relative atomic mass of isotope X is 85.56. So I simply need to look at the periodic table and identify an element, or identify the element that has a relative atomic mass as close to 85.56. And if I look at the periodic table, there are 2 possibilities. In fact, there's just one. Rubidium. Rubidium has 37. Whoops. Rubidium is shown as 37 Rb, and it has a relative atomic mass of 85.5. This is the closest value, 85.5, to the relative atomic mass that we've calculated. Therefore, our answer must be rubidium. Again, really straightforward. Nothing difficult whatsoever, folks. Nothing whatsoever. Okay, so question number 3, done. Moving on to question number 4. You've been told that antimony has the atomic number 51. You're told that the relative atomic mass question is 121.8. This time you're asked to define what's meant by the term relative atomic mass, and you'll see that it's worth 3 marks, which is quite a lot. for a definition. And it's really important that there are certain definitions that your exam board requires you to learn. And that's a non-negotiable. You must absolutely learn it because the examiner is simply giving you the marks there. If you do not know the definition verbatim, word for word, you need to memorize it. Commit time to memorize. Use flashcards, whatever method works for you, whether look and cover, it doesn't really matter ultimately, but learn them. It's really important that you're not losing silly marks like this. Okay, so what is meant by the relative atomic mass? It's simply the weighted mean mass of an atom of an element compared to 1/12 the mass of a carbon-12 atom. Compared to 1/12 the mass of an atom of carbon-12. And if you're wondering why is it carbon-12, well, carbon-12 has 12 nucleons, in other words 6 protons, 6 neutrons, so it's compared to 1 nucleon, of which protons and neutrons have a, well, they're not exactly the same mass, but they're assumed to be. It's just simple. It's simply a definition. Yes, it's a bit iffy. Anyway, where do you get the marks? You get the marks for stating weighted mean. You get another mark for comparing it to 1/12, and you must have the mass of an atom of carbon-12. Couple of points that students often miss out in this definition. They either miss out weighted or mean, both of which is important, and in fact they even miss out mass. They often forget to compare it to 1/12 the mass of an atom. That's the second point that they miss out, and it's really important that you show all the words that I've shown in my definition here. Again, 3 marks, really easy. No reason for you to be losing marks there. Anywho, question number 2. You're told that a sample of antimony of relative atomic mass 121.8 was analysed and it was found to contain 60% of 121 antimony and 1 other isotope. You're asked to determine the mass number of the other isotope in a sample of antimony. Again, got 2 isotopes, same formula that we're going to use. So AR is equal to, so in fact, I'm not going to write the equation down for 2 reasons. It's a 1 marker, I don't have enough space, and it's just a bit silly to do so, seeing as I've covered it in detail before this now. So I'm simply going to write down the relative atomic mass was 121.8, and that should be equal to the percentage of isotope number 1. So let's assume the percentage of isotope number 1, let's assume 121 antimony is isotope number 1. So we've got 60% of that multiplied by 121, and we're gonna do plus. Now, if we've got our sample made up of 2 isotopes, one of which is 60%, then it so follows that the other isotope must be 40%. So 40 times, now we don't know what the mass number of isotope number 2 is. That's what we're working out. So we're gonna, again, if we don't know the number of something, mathematically speaking, use algebra. So again, any letter, I'm gonna choose X again. Right, divided by 100. So we're simply going to gather the like terms, going to take the 100 to the other side. So this part becomes 12180. 60 times 121 is equal to 7,260 plus 40x. So gather the like terms now. So we've got 12180 minus 7260 to give us 40x. So that's 12180. Minus that gives us 4,920 divided by 40, because we've got 40x should equal x. So 4,920 divided by 40 gives us 123. Therefore, x is equal to 123. This is the mass number of isotope number 2. Let's just have a look at whether this mass number makes sense. We know that antimony has a relative atomic mass of 121.8. We know that one isotope has a mass number of 121. The other isotope we've calculated as a mass number of 1, 2, 3. That seems reasonable. If it was, for example, 1, 5, 6, it wouldn't make sense. But because it's close to the other isotopic number, it makes sense. So again, 1 mark for that. Really quite easy. I'm sure you're beginning to feel a little bit more confident on this, if you weren't already, that is. Okay, question number 5. You're told that a salt was used as a fertilizer and it had an empirical formula of H4N2O3. You're asked to suggest the formulae of the ions present in the salt. Firstly, let's talk about what empirical formula means. It's the simplest whole number ratio of atoms of each element in a compound. It's the simplest whole number ratio. So H4N2O3 is our simplest whole number ratio of our fertilizer. We're asked to suggest the formulae of the ions present in this salt. Well, how are we going to do this? Okay, so if we're asked to suggest the ions in this formulae, our formula will contain 2 ions, a positive ion and a negative ion. So having a look at this, we've got H4N2O3. It's easy to make the mistake of assuming that, oh, we're going to have 3 elemental ions. So we're going to have H+, we're going to have N3-, we're going to have O2-, but that doesn't make sense because we've got 2 negative ions, 1 positive ion. So it's important that we break this down and we think about, okay, what other ions have I looked at in chemistry which aren't necessarily elementally based? Well, let's consider complex ions. Well, not complex ions in transition chemistry, but basic complex ions. We know we need to find something that contains both nitrogen and hydrogen, or nitrogen and oxygen, or oxygen and hydrogen. So we've got hydroxide. So we've got OH- potentially. We've got nitrogen and hydrogen, so we've got NH4 pluses. We've got nitrogen and oxygen, which is NO3-, and I can't think of any others, to be honest. Now, out of these 2, which one is it going to be? Well, it's clearly going to be the... Seeing as we've got 2 nitrogens, we've got 4 hydrogens, and we've got 3 oxygens, it must be the NH4 plus and the NO3-. It cannot be the NH4 plus and the OH- because the atoms, the number of atoms in the empirical formula simply doesn't match up. So the ions must be NH4 plus, the ammonium ion, and the nitrate ion, NO3-. I know personally students find this question quite tricky, but it's always important to break it down and apply what you know to a question. Okay, so again, a mark for each one. So 1 mark, 1 mark. Happy days, easy. Moving on, question number 6. You're told, now we're coming on to the multiple choice questions, and I often tell my students that multiple choice questions, they look easy, but they're actually quite difficult at times. So let's see how this one is. We're told, or we're asked rather, what is the formula of the chromium-free sulfate ion? So we are told in the question that there are 4 possibilities. Firstly, let's have a look at the name. Chromium-free in Roman numerals within brackets. That tells us the oxidation state of chromium. In other words, it tells us the charge of chromium ions. Now, chromium is a metal, therefore it must form positive ions. So it has to be chromium is going to form 3+ ions, and sulfate. Sulfate is an ion you simply must know the formula of, so it's SO4 2-. So we've got the 2 ions there. So what must the formula be? To balance the charges, we clearly need to have Cr2 and SO4, and that's going to be 3 times. So let's see which one that is. Cr2, SO4, 3. It's C, so C is our answer there. Again, happy days, really straightforward. Okay, moving on to question number 7, another multiple choice question. What is the formula of ammonium sulfide? So we're going to start off by identifying the formulae of ammonium and sulfide ions. So ammonium we've looked at previously is NH4 positive. Now, sulfide is really important that you do not get sulfide confused with sulfate. Sulfate is SO4 2-. Sulfide, if an ion ends in IDE, it's representing the actual element. For example, oxide is simply the oxygen ion, O2-. Nitride, nitrogen, N3-. Sulfide, it's in group sulfur, it's in group 6, so it has 6 outer electrons, so it must gain 2 more to have a full outer shell, so it's going to be S2-. So again, if we were to work out the formula of this, we'd need 2 ammonium ions for every sulfur ion. So that's our formula there, NH4 2S. So if we identify that, that's also C in the question, and again, that's just 1 mark. I believe students often chose, when this exam question came out, a lot of students chose that as the answer because they got this confused with sulfate, or they made the mistake of misreading the question ultimately. Okay, moving on. Let's have a look. The electron configuration of element X is 1s2, 2s2, 2p6, 3s2, 3p4. What is the formula of a compound formed when sodium reacts with element X? Okay, so sodium is in group 1. It's going to form Na plus ions, right? So we've got Na plus ions. Now we've been told that the electron configuration of our element X ends in 3p4. Already suggestive that it's in the p block because the highest energy electron is in the p orbital. And it's going to be in group 4, the 4th column of the p block. So that includes groups 3, 4, 5, and 6. And in fact, it's going to be in group 6 because that's the 4th group in the p block. So if we know it's in the 4th group, and the 4th of the p block, that is, the 4th group being group number 6, then that means if X is an atom that belongs in group 6, it must have 6 valence electrons, 6 outer shell electrons. Therefore, it must gain 2 to obtain a full shell of electrons, meaning it must have a 2- charge in its ion. So we've got X 2-. So our formula will simply be Na2X, and Na2X is again C. This is coincidence. Okay, so we've got a mark there. Really straightforward. I'm saying that too often. Okay, so I appreciate it might not be. So, okay, barium nitride is formed when. So, question number 9. Barium nitride is formed when barium is heated with nitrogen. Complete the electron configuration of a nitride ion. Okay, so let's start off. What is nitride? We know it's an ion of nitrogen. We know it's simply nitrogen, nothing else, like NO3. For example, nitrate is NO3-. It's not got 2 elements, it's just 1 because it ends in IDE. Now, nitrogen is in group 5 of the periodic table, meaning it has 5 valence electrons in the outer shell of nitrogen. So for nitrogen to have a full outer shell, it's got to gain 3 more electrons. So the formula of nitride must be N3-. So if we have a look in the periodic table, nitrogen is actually shown as N7 and 14. So it has 7 electrons in the outer shell. It has 7 electrons in total. So if we've got an ion of nitride, which is N3-, we've gained 3 more electrons. So that brings our total number of electrons to 10. So we've got 10 electrons in the outer shell. So 10 electrons. Sorry, I beg your pardon, 10 electrons in total. So we've got 1s2, that's 2 electrons. The next shell that's filled is 2s2. We've got a total of 4 electrons. 2p, now we've got a total of 10 electrons, therefore our p orbital must have 6 electrons in total, and that just works out because the p orbitals can hold, sorry, I beg your pardon, the p subshell can hold a total of 6 electrons anyway. Okay, so 2, 4, 6. So 2, 4 plus 6, 10. So that gives us a total of 10 electrons. Again, that's our answer for the electron configuration of nitride ion. Now we're finally on to the last question. I know it's taken us a while to get there. So, solid Barium nitride is reacted with water, forming an alkaline solution of A and an alkaline gas B. And immediately it's a 4-mark question, so that's considerable. Identify A and B, write an equation including state symbols for the reaction. Okay, so let's start off with writing the formula of barium nitride. What is it? So we know that barium has a symbol Ba, and barium is in group 2, so it forms 2+ ions. We know nitride in barium nitride is based on nitrogen. We've already established it has the formula M3-. Therefore, the formula of barium nitride must be Ba3N2, because we need 3 of the 2+ ions to give us a total charge of 6+. We need 2 of the N3- to give us a total charge of 6-. So they cancel out. Ba3N2. Now, Ba3N2 reacts with water. I'm going to start with an equation, to be honest. So I'm going to write down Ba3N2. But it asks us for the state symbols, so we must show this. So we're told that it's solid. So solid state symbol plus water. Now, water is obviously H2O. State symbol for water is liquid. And it goes to form 2 substances. Okay, so what knowledge are we drawing on here? So you'll have covered that group 2 metals react with water to make hydroxide solutions. So barium would react with water to make barium hydroxide. And it turns out that all hydroxides are alkaline because they release OH- ions. So that's our alkaline solution. So barium hydroxide. Now we know that barium has a 2+ charge, so we know that hydroxide has an OH- single minus charge. So the formula of barium hydroxide is simply going to be, it's simply going to be Ba, beg your pardon, BaOH2. Now that is a solution, so it's going to be aqueous. And therefore, our aqueous solution has been figured out. The identity of that has been figured out. It's simply BaOH2. That's our alkali solution A. Okay, so what's the nitrogen going to do with the water? Well, we're told that this produces an alkaline gas. The only gas that I can think of that's alkaline is ammonium. Oh, sorry, NH3, because ammonium would be an ion. NH3. So we've got NH, and that makes sense because the nitrogen in nitride will react with the hydrogen in the water. So we've got NH3. Because it's a gas, we need to show the state symbol G. Okay, now we simply need to balance this equation because it does ask us, oh wait, no it doesn't. Okay, so let's have a look. It doesn't actually tell us to balance the equation for this. It does tell us though to identify the 2 substances. So let's identify the alkaline gas as ammonia. So I've got that. I've worked out that A is barium hydroxide. I've worked out that B is ammonia. I've written an equation including the state symbols, but I'm told that there's 4 marks in this question, and I very much doubt that you're going to get a mark for the equation and a mark for the state symbol. So we're going to balance the equation. Despite you not telling us to, we're going to do so because it's good practice, especially when you can figure out from the number of marks that there might be something going on here. So let's see, how am I going to balance this equation? Well, on the left hand side I've got 3 bariums, on the right hand side I've got 1. So I'm going to stick a large 3 in front of the barium hydroxide there. Okay, I've got 2 nitrogens on the left hand side in barium nitride, and I've got 1 nitrogen on the right hand side for ammonia. So I'm going to stick a large number 2 in front of the ammonia there. Let's have a look at what's worked out. So barium's balanced, nitrogen's balanced, hydrogens. I've got 2 hydrogens on the left hand side in the H2O, and I've got a considerable number of hydrogens on the right. Let's work out. I've got 2 in every barium hydroxide. There are 3 barium hydroxides, so that gives us a total of 6 hydrogens. I've got, so we've got 6 H's over here, and in every molecule of NH3 I've got 3 hydrogens, therefore in 2 I've got another 6 hydrogens, so we've got a total of 12 hydrogens on the right hand side, we've got a total of 2 on the left hand side, so we need to have a large number 6 in front of the H2O. And this equation is now balanced, and we've got state symbols, so we're going to get a mark for the equation and a mark for the balancing. So that's 4 marks right there. Okay, well, I hope that was useful. If you are, or if you have come to this point, well done, and I suppose we'll carry on in the next video. See you then. Have a good one. Bye.